Here is a list of 30 algorithms along with short descriptions of how they work and how you would implement them without diving into code. 1. Binary search. Description: efficiently finds the position of a target value within a sorted array by repeatedly dividing the search interval in half. Implementation: start by checking the middle element. If the target value equals the middle element, return the index. If the target is smaller, search the left half. If larger, search the right half. Repeat until the element is found or the interval is empty. 2. Bubble sort. Description: repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. Implementation: start at the beginning of the array, compare each pair of adjacent elements, and swap them if they are out of order. Continue until no swaps are needed, which means the array is sorted. 3. Merge sort. Description: a divide and conquer algorithm that divides the array into halves, recursively sorts each half, and then merges the sorted halves. Implementation: recursively split the array into halves until each subarray has one element, then merge subarrays back together in sorted order. 4. Quicksort. Description: another divide and conquer algorithm that selects a pivot element, partitions the array into two halves, elements smaller than the pivot and elements greater, and recursively sorts the halves. Implementation: choose a pivot, partition the array around the pivot, then recursively apply quicksort to the subarrays. 5. Selection sort. Description: repeatedly selects the smallest, or largest, element from the unsorted portion of the array and swaps it with the first unsorted element. Implementation: find the smallest element in the array and swap it with the first element. Move to the next element and repeat for the rest of the array. 6. Insertion sort. Description: builds a sorted array one element at a time by inserting each new element into its correct position. Implementation: start from the second element, compare it to the previous elements, and insert it in its correct position. Repeat this process for all elements. 7. Heap sort. Description: sorts an array by first turning it into a max heap, binary tree, and then repeatedly extracting the maximum element from the heap. Implementation: build a max heap from the array, then remove the root, maximum element, place it at the end of the array, and restore the heap property for the remaining elements. 8. Breadth first search. BFS. Description: explores all nodes of a graph level by level starting from a given node. Implementation: use a queue to explore the starting node, then enqueue its neighbors. To queue a node, visit it, and enqueue its unvisited neighbors, repeating this process. 9. Depth first search. DFS. Description: explores a graph by going as deep as possible along each branch before backtracking. Implementation: use a stack or recursion to explore the starting node. For each node, visit an unvisited neighbor, push it onto the stack, and repeat until there are no more neighbors. 10. Dijkstra's algorithm. Description: finds the shortest path from a starting node to all other nodes in a weighted graph. Implementation: use a priority queue to explore the starting node. For each node, calculate the distance to its neighbors, update the shortest known distance, and repeat until all nodes are visited. 11. A search algorithm. Description: finds the shortest path in a graph using heuristics to guide its search, prioritizing paths that seem most promising. Implementation: combine Dijkstra's algorithm with a heuristic function that estimates the remaining distance to the target, using a priority queue to always expand the node with the lowest cost plus heuristic value. 12. Floyd-Warshall algorithm. Description: finds shortest paths between all pairs of nodes in a weighted graph. Implementation: use dynamic programming to update the shortest path between each pair of nodes by considering intermediate nodes one by one. 13. Bellman-Ford algorithm. Description: finds the shortest paths from a single source node to all other nodes, even if the graph contains negative weight edges. Implementation: initialize the distance to the source as 0 and all other nodes as infinite. For each edge, relax it by updating the distance if a shorter path is found. Repeat this process for each node. 14. Kruskal's algorithm. Description: finds the minimum spanning tree, MST, of a graph using a greedy approach by adding edges with the smallest weight. Implementation: sort all edges by weight, and add the smallest edge to the MST, ensuring no cycles are formed. Repeat until the MST contains all vertices. 15. Prim's algorithm. Description: another greedy algorithm for finding the minimum spanning tree, starting from an arbitrary vertex and adding the smallest edge that connects to an unvisited vertex. Implementation: start from any vertex, add it to the MST, and add the smallest edge connecting the MST to an unvisited vertex. Repeat until all vertices are included. 16. Topological sort. Description: orders vertices in a directed acyclic graph, DAG, such that for every directed edge from vertex A to vertex B, A appears before B. Implementation: use DFS, and as each vertex finishes exploring, add it to a stack. After all vertices are explored, the stack gives the topological order. 17. Knuth-Morris-Pratt, KMP, algorithm. Description: a pattern matching algorithm that searches for a substring in a text using a partial match table to avoid re-evaluating characters. Implementation: build a partial match table, failure function, for the pattern. Use it to skip comparisons when a mismatch occurs between the text and pattern. 18. Rabin-Karp algorithm. Description: a string searching algorithm that uses hashing to find any one of a set of pattern strings in a text. Implementation: compute the hash for the pattern and for substrings of the text. If the hash matches, compare the substrings to confirm the match. 19. Dynamic programming, DP, Fibonacci. Description: finds the nth Fibonacci number by storing previous results and using them to compute the next one. Implementation: start with the base cases, f0 equals 0, f1 equals 1. Use these to compute fn iteratively or recursively by storing intermediate results to avoid redundant calculations. 20. Dynamic programming, longest common subsequence, LCS. Description: finds the longest subsequence common to two sequences. Implementation: use a 2D table to compare each character in the two sequences. Fill the table with the length of the LCS up to each point by comparing previous subsequences. 21. Dynamic programming, knapsack problem. Description: solves the problem of selecting items with given weights and values to maximize value within a weight limit. Implementation: use a 2D table to store the maximum value for each combination of items and weight limits. Build the solution by choosing to include or exclude each item. 22. Greedy algorithm, activity selection. Description: selects the maximum number of activities that can be performed without overlapping, given start and end times. Implementation: sort the activities by their finish time, and select the first activity that finishes earliest. Then, select the next non-overlapping activity. 23. Greedy algorithm, coin change. Description: finds the minimum number of coins needed to make a given amount using a set of coin denominations. Implementation: start with the largest coin denomination and take as many of those coins as possible. Then move to the next largest denomination until the amount is reached. 24. Sliding window algorithm. Description: efficiently calculates sums, averages, or other aggregate functions over a fixed size window in a data stream. Implementation: keep track of the current sum, or other metric, for the window. As the window slides to the next position, subtract the element that leaves the window and add the element that enters. 25. Divide and conquer, closest pair of points. Description: finds the closest pair of points in a set by dividing the points into halves and combining the closest pairs from each half. Implementation: split the points by a median line, recursively find the closest pair in each half, and then check for any closer pairs that straddle the dividing line. 26. Backtracking, n-queens problem. Description: places n queens on an nxn chessboard such that no two queens attack each other. Implementation: start placing queens one by one in each row, checking if the current position is safe, i.e., no queens threaten each other. If a safe position is found, move to the next row. Bellman-Ford algorithm. Description: solves the shortest path problem in graphs with negative edge weights. Implementation: iterate over all edges and update the distance for each node repeatedly, allowing negative edge relaxations. 28. Union find, disjoint set. Description: a data structure that keeps track of elements split into disjoint sets and supports union and find operations. Implementation: use an array where each element points to its parent. The root represents the set. Implement union by connecting roots and find by following parent pointers. 29. Flood-fill algorithm. Description: fills a connected area with a color starting from a given pixel. Implementation: use DFS or BFS to explore and recolor all adjacent pixels that share the same color as the starting pixel. 30. Z algorithm for pattern matching. Description: finds all occurrences of a pattern in a text by pre-processing the pattern into a Z array that stores lengths of matches between the pattern and substrings. Implementation: construct the Z array for the pattern and text combined, and use it to find positions where the pattern matches the text. These algorithms cover a broad spectrum of problem-solving techniques and are foundational to understanding more advanced algorithms and data structures.